I was getting ready to put everything together so we could start running these tests, but then I realized I got one quick setback, and that's going to take me about an hour or so, and that is to wire up this PID I had almost finished. And the reason for that is that I needed a method, a means to track the temperature, and I want to track it digitally. My port takes a K-type thermal probe, so I actually needed sort of like a PID type of a controller so I could do that, because I can run this in manual mode, which means that it's on 100% of the time, just like plugging the element into the wall. So I'm wiring this up. I'll have this done here real shortly, and then we'll go right into running the test, because the benefit is now I've got a PID that I can run in PID function, and so I can run some additional tests for demonstration as well. One drop will make a rabbit whip a bulldog. Taste will make a rat whip a wild hog. My controller's ready to go. I'm ready to go. And here's how we're going to do this. I've got to run several tests, so this will take me the majority of today. I've used that 8-gallon kettle, just like we discussed. Now, instead of using that long column that a lot of us are accustomed to, some of you may have this. This is the traditional pot still head. And the reason I'm going to use this is because it gives me an instant, almost not, well, not an instant data point, but it gives me a data point closer to the top of the kettle, and you can kind of extrapolate that. And remember, we did a video some time ago on insulating the column in order to prevent that loss of energy as well. But now we're going to insulate the kettle, and we're going to try to find out what the difference is and how much efficiency we can gain. So let me get this started and explain briefly. If you can recall, we also did a video on how long should it take based on the element you're using. We're going to use a heater element as opposed to propane, but propane works the same way. You can use the same formula, and you can recall from that video, this was the formula, but don't let that dissuade you, because it's not that difficult. It's volume in gallons times 8.33, and that's 8.3 pounds per gallon. And for those of you in the more, I guess, intellectual world, all of this can be converted into metric, which is so much easier to use. Okay, then we'll multiply that by our change in temperature, which is the final temperature minus the starting temperature. And then we'll divide that by kilowatts times 3413, which is the number of BTUs in a kilowatt. And that will give us the time it should take, all things being equal, the time it should take to heat that much of a liquid. All right, and in this case we use water as our base data point because a gallon of water does not equal the same as a gallon of ethanol. We went through that on that video. All right, I have 3 gallons. So what that really means, in fact, is that I have 3 times 8.33 equals, this will equal 24.99. Can we just use 25? 25 pounds. Now our temperature change, we want to get to 175, and the water that I'm using, and I've already measured that, and that's pretty standard about this time of year, is 53 degrees Fahrenheit. Oh yes, in the plumbing. So the difference between that is 122 degrees. That's how many degrees I want to raise 25 pounds of water. So this is the figure that goes right here. So 25 pounds times 122 degrees Fahrenheit equals 3048.78. And now we're going to divide that by, see how simple this gets? We're going to divide that by kilowatts times 3413. And I'm using a 2.5, a 2500 watt element on 240 volts. So 2.5 times 3413 equals 8532.5. So, in final, this number divided by this number should give me the time it should take, okay, because this is BTUs per gallon per, yeah, you follow it. 3048.78 divided by 8532.5 equals 35.7 minutes. So I'm getting, well, if we can round this off, 36 minutes is how long it should take a 2500 watt element to heat 3 gallons of water by 122 degrees. Let's give that a try. Now, consider this as well. We're not going to insulate this. We're just going to run it the way it is. And remember, by the way, one other thing you need to know, just because your data, your results may differ from mine. It is right now, it is 71 degrees Fahrenheit inside the shop. Okay, the ambient temperature. And that makes a difference because the amount of heat loss depends on a couple of different factors. One is the temperature inside, the coefficient or the amount of thermal energy that can be conducted by a material, the thickness of that material, and the temperature difference on the outside. And that's another long formula that we're not even going to concern ourselves with, but those are the three things primarily that is going to control the amount of time it takes. And so we already know what the temperature inside, okay, we know how much there's in there, but the temperature, and what we don't know is we haven't figured out what is the coefficient of this stainless steel, but it's going to kind of give us an indicator when we get our results. But the temperature on the outside. So if the temperature on the outside is a whole lot cooler, it would probably just take longer. Or if it was a lot warmer on the outside, it would not take as long. So that is a factor to consider. Your results may be a little bit different when you run a test. Now, to be as precise as possible, I've measured, I've got it filled with 3 gallons of water, and I knew that there was going to be a potential of a change in temperature, so I filled it up first. I'll let the stainless steel become cold, dump that, and then filled it with 3 gallons of water. And it's 59 degrees, so there's a little bit of a temperature difference between what comes out of my spigot and what's sitting in here, and of course then I've got the ambient temperature. So that is now the difference. This is 59, and so my difference is actually 116. So if I change this to 116, my result is now 2900, and if I divide that by 8532.5, that brings me down to 34 minutes. So at 34 minutes is my mark now that I'm looking for. That's how long it should take, all things being equal. Well, let's find out. Now the first thing I've done, I've got this filled, I've got everything assembled, I've got my thermocouple in there, because I'm going to use this dial, this digital output, to tell me exactly when it gets to 175. Now, in order to make, I'm going to use my PID in manual mode, and what that means is I'm just going to I'm bypassing the P, I, and D function. I'm just going to turn this thing on 100%. And to do that, if you've got one of these Inkbirds, the Inkbird 106 VH, just push the AT run button. Hold it until that green light comes on. And once the green light comes on, push set one time, and there it shows up as 100. But you can go up and down, and I can set the amount of power. And the power output right now is 100%. So it's going to be on totally, and it won't fluctuate anything. Because hell, if it fluctuated, it wouldn't tell me what I'm looking for. Now it's time to plug it in and get my stopwatch going. So from the time that I plug it in, I'll start the stopwatch. And we'll see just how long it takes for that to get to 175 degrees right here. We are at just about 33 minutes, and I'm at 166. Let's see how long this takes. It's not as fast as it probably should be, but I know we're losing. Yeah, that's pretty hot. So there we are, 175 degrees at 39 minutes. 39 and a couple of seconds, there's some change. So it took us 39 minutes to get to 175 degrees, which is an indicator of efficiency. Plain and simple. We calculated 34, it took us total time of 39. Let's see what happens on the next test. All right, now we're getting ready to start the second time. And this time I've got it wrapped in my thermal blanket, and I've got the blanket that I made also to set it down on so I didn't lose any thermal energy out of the bottom. So let's find out what the difference is. Start. Time will tell. I was quick. I just turned this off at 175.1, and it came out at 24:46. What's it? 25 minutes. So that's a big difference. 25 minutes. 34 is the calculated time, and this one is insulated. So there's my difference. What we need to do now is we need to graph this to just real quick, just so we can get an idea of what the real difference is. And I think it shows you, to me right now, that the blanket around here and the blanket here insulating this, can you just imagine what the difference would have been in efficiency if we also insulated a column? Because there is some heat loss there. So this has been a really fun experiment. And let's check our data points and find out what we got. So what did I learn from that? Well, I learned that I've actually improved the efficiency of that system by 36%. Yeah, that's friggin' amazing. I graphed this out so you can get an idea. You can see, and these are all my data points. And this is the difference between an insulated and an uninsulated column. And as a matter of fact, when I insulated the column, I had to collect a few extra data points because things were going so quick. So you'll see here that we started at 59 degrees with both of them. And then in 12 minutes, I was at 81 degrees and 85 degrees, respectively, uninsulated and insulated. And then it kind of remained the same, 92 to 96 at 15 minutes. At 18 minutes, we were at, what was that, 92 and 90. Oh, there we go. Yeah, whoa. Yeah, and at 18 minutes, we were at 117, 116. And this is sort of like, that was an anomaly there. I mean, it should have been actually reversed. It doesn't matter. It doesn't matter. But from that point on, there was a definite difference in the reduction of heat loss and heat that was retained inside that system. Because if you'll notice here, I had to take a measurement. At 23 minutes, I was already at 162, and 24 minutes, I was at 171. And you'll notice here at 25 minutes, I was only at 150. And it took from 25 minutes to 31 minutes, I was at 160. Oh, there's my mark. Yep, 160. And then at 39 minutes, of course, I was at 175. But in the insulated one, I managed to achieve a full 175 degrees in, where is that? There we go, 25 minutes total. 25 minutes from start to 175 degrees. So there's that difference between 39 and 25. If you divide 39 into 25, it's like 64. So, and the remainder of that is the improvement of the efficiency. If I think, okay, I get it. It's only supposed to take, it was supposed to take 34 minutes, but I've got this thing whittled down to 25 minutes. And maybe somebody else can help explain this, but I got to think about this one for a while. I know that by demonstration, I've made one hell of an impact on the time it takes to go from 59 degrees to 175. Matter of fact, it's so efficient, it is below what the calculated value should have been, which kind of, I don't know, maybe someone else out there can explain exactly why that is. I know there's a difference between the liquid and the vapor. I mean, I got all of that and thinking through it. It's, but that's amazing. That's amazing. And just remember that if you're not losing heat before you want to lose heat, well, then your system runs a whole lot smoother, and controlling that volume and that energy becomes much less problematic. So it's smoother transitions, and your system and your process will run that much smoother. Not to mention the cost savings involved with putting all that energy in there. Happy distilling.